Well, let's get started this week looking at the light emission chapter. Um, Continuing on from surface reflection, and actually I don't want full screen because then I can't see tabs if I have them. Um, I wanted to go two chapters back because this one has all the radiometry stuff and it's a useful reference. Okay, so atoms are always moving. Unless they're at absolute zero, at which is, I think it's physically impossible to reach, like laws of physics impossible. But uh, then we throw in some Maxwell's equations and we get electromagnetic radiation at room temperature. Most of the most of the emission is infrared. It needs to be hotter to emit light in the visible frequency. We call things that create light a lamp or an illuminant. Oh, for the spectral distribution of emission. Okay, that's I've never heard the term illuminant before, so uh interesting that it could also be is a synonym for lamp, but apparently it's used here for spectral distribution of emission. I believe this is French, luminaire. This is more technical detail about household furniture than I have ever thought I needed, especially for a textbook about computer graphics, but I digress.
Wait till you see the later list. That's just
Oh,
baffled me so much.
oh boy. Okay, well, I'll try not to spend too much time on things that are more mundane. Uh, four different types of lights. We got incandescent, halogen lamps, gas discharge lamps, and LED lights. Um, Incandescent heats something up to be really hot and then emits light because it's just really hot and also emits a lot of heat. And that's why it sucks for energy efficiency. But it's good for other things like broad spectrum emission. Um, halogen, halogen gas. So wait, is halogen just like a fancy form of incandescent light bulb? Because it's filled with halogen gas? Or is this a neon light?
It's a halogen light.
Oh, I guess it is a halogen.
I think it's just because neon's just a different type of gas, right?
Uh, Interesting. I guess this is, I'm thinking like complex fluorescent lamps, which is where they use fluorescence. Um, Gas discharge lamp. Okay, so gas discharge lamps are fluorescent lamps. Uh, oh, hydrogen, neon, argon, vaporized metal gas. So neon lights are just a fluorescent light, but a specific kind of it, rather than a white light. Neon for different colors and stuff. Okay, and then they get broadening. Um, is does this what about sodium? So I'm thinking, where's the search bar? Low pressure s- sodium vapor lamp. Okay, it's also a gas discharge lamp. that uses sodium. Okay. This is like I think it's the low pressure sodium ones are the ones that street lights are often, at least on older times, that characteristic orange glow because it like emits light at the 589 nanometer and that's it because it's fluorescing. Anyways, okay. And then we have LED lights, which are awesome and we should always use all the time, except when we shouldn't. Um, yeah. Electrons collide with atoms, pushes outer electrons to their highest energy level, and when it returns to the lower energy level, photon is emitted. Uh, there's more ways to make light, but we're not worried about it. Luminous efficacy. How effectively a light source converts power to visible illumination, accounting for the fact that human observers' emission in non-visible wavelengths is of little value. Ratio of photometric. It is the ratio of a photometric quantity to a radiometric quantity. Ah, yeah. Interesting. So we have the luminous efficacy, we have the uh spectral response curve. I mean, it's just like measuring how much power you put in it versus how much visible light comes out of it. Lumens per watt. Uh, I I find this interesting because in if we're only trying to simulate light, then it's of questionable importance to also understand how much, electrical power or heat energy is being put in or coming out of the system. Because we're not really worrying about that. Like we're not worrying about simulating the effect of heating up the surface due to the bright hot light. Or are we? No. Ratio of luminous excitance to irradiance. Okay. Radiant, okay. Photometric radiant excitance to the uh radiometric irradiance. Okay. Um, so incandescent tungsten light bulb is 15 lumens per watt. The wavelength can go up to 683 nanometers. I'm not sure what this is saying. Okay.
Yeah, I also don't understand what's the point. Like, why it's unpleasant for human if it's so efficient.
What is 683? What are the units? What is it referring to?
Is that
I
the
think
lumens
it's
per
just
watt?
lumens per watt.
Yeah.
Yeah, because they said 15 before.
Okay. Okay, well, okay. Well, I'm not too worried about it, but okay, black body emitters. A black body emitter is a perfect emitter. I do find the word black body to be kind of a misnomer because a black body is only black if it's below a certain temperature. Otherwise, it's no longer black, but it's, like emitting visible wavelengths of light. Therefore, it's not black. Um, Still converts power to electromagnetic radiation as efficiently as physically possible. Huh, I've not heard of black body emitters being perfectly efficient or, being something close to it. But I guess that kind of depends on frame of reference for what you're talking about efficiency. Okay. Black bodies are called that because they absorb absolutely all incident power, reflecting none of it? Okay. Oh, okay. Is a black body emitter a hypothetical thing, not a real world thing? Oh, then I've been confused.
Yeah, black body is just a term from physics, but we often model light this way, right? We often, when we model light, we just don't consider their reflection.
Yeah. If time was reversed, a perfectly absorbed power would be efficiently re-emitted. That's a way to put it. So we got Planck's law. Given the radiance emitted by a black body function as a function of wavelength and temperature measured in kelvins. So this is your black body radiation equation. We give a wavelength and a temperature, and it's equal to 2 times Planck's constant times the speed of light squared divided by the wavelength to the fifth power times e to this whole thing where k of b is Boltzmann constant minus 1. T is the temperature. Okay, there's the temperature. Okay. Oh, okay. So at different temperatures, so this is a two variable equation. Do we have to give it two temperatures? Or we fix the temp. Okay, so each one of these graphs fix the temperature at, like 4,500 Kelvin and vary the wavelength across the visible spectrum and near infrared. And as you decrease the wavelength, i.e., increase the energy of each photon, um, wait, why is it going down? Emitted radiance distributions for a number of temperatures. Oh, it's going down because it's emitting less light at a particular frequency. So we can see that the 4,500, most of its energy is, being emitted in the like 500 to 800 nanometer range. And as there's less and less light being emitted at those wavelengths at that temperature. And at 3,000 Kelvin, it's significantly further to the right because that's the higher wavelength. That's more infrared. And I bet the shape of this curve is similar, where it has a peak, but we can't see the trail of it because it gets cut off. And 3,000 is so shallow that barely any of it gets emitted at a visible wavelength, which is why it's a deep orange, deep red color versus T 4,500 where it's all the way down to blue wavelengths. So you get a more white curve because it's across all three, red, blue, and green. Okay. Oh yeah. I didn't read this paragraph, but I think I said mostly what was said here. Um, if you ever want to calculate this, you have fun things like 10 to the, uh, 3 times 10 to the eighth power and Planck's constant, which is 6 times 10 to the negative 34th, and the Boltzmann constant 10 to the negative 23. Because these numbers are tiny and speed of light is big. So that's a lot of fun math to do if you're having to do a physics problem in class because you don't have access to a calculator. I'm not bitter, definitely not. Okay, The blackbody function computes emitted radiance at a given temperature for a given wavelength. So we just implement this function or this equation here in here. The wavelength is in nanometers, but the constants are in terms of meters. We have to first convert it. That's fun. Then we just have all that math. It's the fifth power of the wavelength. That's divided by the fifth power. So um, the energy emitted, the higher the yeah. I'm just thinking the fifth power is a very large power.
Yeah, but we have exponential, so that's why wavelengths when we go to 0, then the exponential go to like infinitely.
Okay. Okay. Yeah.
Yeah, that's why we still get 0 emission when the wavelength is 0.
Somehow that makes intuitive sense, but if you just try to show me the equation, I would not have intuitively thought of that. At least I didn't just now, so what do I know? Okay, we have non-black body emission is described by Kirchhoff's law. Emitted radiance distributed at any frequency is equal to the emission of a perfect black body at that frequency times the fraction of incident radiance at that frequency that is absorbed by the object. Oh, and it's at thermal equilibrium, which, is a useful thing to be able to assume away. So the fraction of radiance absorbed is equal to 1 minus the amount reflected. That's times the... Wait, I need to reread this. It's emission of a perfect black body times the fraction of incident radiance at that frequency. Oh, okay. So the reflected radiance is proportional to the absorbed radiance by 1 minus the reflected radiance. Okay. So whatever light isn't reflected is absorbed, is what this means. It's interesting that we're multiplying it by the black body radiance. Hmm. Okay, we have Stefan-Boltzmann law, radiant excitance or outgoing irradiance at point P for a black body emitter. You know, I was thinking of the Stefan-Boltzmann law when I saw the Planck's law. So apparently my intuitive understanding of outgoing power and radiance in irradiance is not super good because I confused everything. Um, so sigma times temperature to the fourth power is the radiant excitance. Oh, so the amount of energy being thrown out by a emitter is proportional to the fourth power of its temperature times Boltzmann constant. Did I say proportional? It's equal to, meaning a 1,000-degree surface versus a 2,000-degree surface. The 2,000-degree surface is putting out 2,000 to the fourth power, versus 1,000 to the fourth power, which is a much bigger number. 2,000 times 2,000 times 2,000, that's 16, 3, 6, 9, 12 to the 16, or 1.6 to the 12th power versus 1,000 to the fourth power, which is like, okay, I'm just coming up with numbers out of the top of my head. Okay, yeah. Doubling the temperature of a black body emitter increases the total energy emitted by a factor of 16. That's what I was trying to get at. So even though a surface that is twice as hot, emits way more energy, 16 times more, which is kind of crazy. Uh, Black body emission provides useful metric describing emission characteristics of non-black body emitters through color temperature. If the shape of emitted spectral distribution is similar to the black body distribution at some temperature, it has a corresponding color temperature. Okay. One way to find color temperature is take the wavelength where the light's emission is highest and find the corresponding temperature using Wien's displacement law. Wien's? I think that's Wien's displacement law. Gives the wavelength where emission of a black body is maximum given its temperature. Okay, so color temperature is just kind of a feel-good thing. We say incandescent lamps are like 2700 K. I've thought that it was the surface of the incandescent filament was 2700 Kelvin, which may be true, but when discussing color temperature, it's more like we associate that orangish hue to be 2700 K and less orangish, more yellowish at 3000, and then you go up to 4000, 5000, it gets progressively more white, and by the time you get to 6000 plus Kelvin, it gets bluer because more of the radiation is in the blue spectrum, or on the bluer side of the visible spectrum, and well, a lot of it is actually probably ultraviolet radiation and at higher temperatures, so higher Kelvin temperatures. Okay, moving on. Categorizing light emission distributions. That Commission Internationale de... I'm not going to try to pronounce that. That's... If anyone's brave enough in the audience to try to pronounce that French word, go ahead. It's 1931, intended to represent average incandescent light. Black body radiator, 2856 Kelvin. Oh, we've improved the accuracy of all the constants, so we had to change it by 6 degrees Kelvin. But we didn't change, we wanted to keep the illuminant value the same, so we just changed the definition a bit. So Power distribution as a function of wavelength in nanometers. So a black body radiator at 2,856 Kelvin emits this amount of power at each wavelength. What's the units for this? Just power? Spectral power distribution. I guess that would be what to use.
Then yeah, there should be power there.
Okay. Okay. The D, so we have the A illuminant, which is this one, and then we have standard D, describes phases of daylight, characteristic vector analysis of daylight spectra, express daylight in terms of linear combination of three terms, with one weight essentially corresponding to the yellow-blue color change due to cloudiness, and the other corresponding to pink-green due to water in the atmosphere. So 6,504 Kelvin is daylight, midday sunlight in Europe. Oh. So it bright sunlight in the middle latitudes, like the tropics and tropical areas, might actually have a brighter color temperature or a higher color temperature than 6,500, just because it's even more directly overhead. Hmm. Okay, European latitudes, yeah. Fluorescence. Oh, yeah, I guess they did have fluorescent lights in 1930s. Whoa, that's some spiky fluorescing. Okay, do we want to go to the next chapter, or are we good for now?
I think we are good for now.
Okay, yeah. Oh, this looks like a long chapter too. Yeah, okay, that's good. I I want to say this chapter feels a bit light on the depth of content, but it is kind of just throwing things like the Planck's, whatever it's called. Where was it? Planck's law and uh this this bad boy for the surface emission and why Wien's displacement. Yeah, it feels like it's being a lot of just physics is being thrown at us without much context or not context, but without much like way to stitch it into something more understandable.
Yeah, I was
Yeah,
gonna say that. I would like to see like a image for before implementing this and after implementing, like what the difference is. That'd be helpful to me.
I don't even think this is something you implement so much as just like this is the physical basis that we use to come up with our formula, our 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 physical basis for light. If that like without it, you just don't have a physically based render, and that's cool. But um, I guess yeah, I'm struggling to try to imagine how you would go about doing everything without this kind of basis.
This
Although,
also kind of reminds me of I forget which studio, but it was like a racing game and they generated their skybox using like all the physics of like the atmosphere and stuff, and they got like really realistic skyboxes that were almost indistinguishable from like photographs.
yeah, I don't know which game that is, but yeah, like my criticism with chart D here is really just it is trying to describe the very complex interaction of our atmosphere and the sun. And you can see how bumpy this is, and there's probably dollars to donuts. I bet you that this has changed in the last 100 years, since 1931, almost 90 years, due to increased CO2 and other pollutants in our atmosphere. How much it's changed is possibly imperceptible to a human eye, but I mean, like, if you're wanting to get super detailed information, it would be kind of interesting to see if it has a noticeable impact on the way light bounces in our atmosphere. Also, there's some fun. I saw a fun video about using the fluorescent light's peak to create a green screen effect. It was pretty cool, but uh, kind of off topic. So yeah, okay. I think we should end it here then.
Sounds good.